All right, cool. And we're recording. So yeah, today we're going to be talking about Dijkstras, minimum spanning trees, what they are, and disjoint sets. So let's begin. As usual, we begin with a few memes. They're a little bit funny once you learn BFS, DFS, Dijkstras, and you start understanding a meme. Yeah. So let's first off with kind of reviewing Dijkstras, and this is going to be kind of look like what y'all were doing on exercise 4. So with Dijkstras, this algorithm is used to find a shortest path between a source node and either every other node or a particular target node. And it's similar to BFS in that BFS is used to find the shortest path, but BFS is used to find the shortest path in terms of number of edges you cross. But Dijkstras is used if you want to find the shortest path in terms of edge weights. So if there are edge weights in your graph, then this is where you might use Dijkstras. And the main idea is that you want to find the shortest path or shortest distance from your start node in the graph to every other node. So let's say I want to find the shortest path from node, let's see, maybe 0 right here to every other node. Then using Dijkstras, I could do that. The shortest distance from 0 to 2 is 1, shortest distance from 0 to 1 is 2, and so on as you follow these paths. And with BFS, it uses a queue, DFS uses a stack, Dijkstras uses a priority queue. And the way the priority works is the priorities of the nodes are their distance from the start node. So if you want to get the shortest distance, then you would pick the shortest path from the current node you're looking at to the source node. So that will be the next path that you will explore. We pull the closest node off the queue at each iteration, and this ensures that you're getting the next shortest path possible. And that is why Dijkstras is called a greedy algorithm, because it picks the shortest possible path you can pick at every single chance, every single iteration it can get. And then you repeat until you try to explore every single node. And of course, there might be some nodes that you can explore, in which case the cost to get to that node from the source would be infinity because you can't even get there. All right, cool. Any questions so far? All right. So, and here's the pseudocode. I won't go too much into it. Y'all can look at it on your own when you're working with it. But essentially, this is the pseudocode. It does exactly what we kind of discussed right here. Here's just the pseudocode for it. Converting into code is basically just copying over what the pseudocode says and just writing it into code. Now, question: how to get the shortest path? Answer: after running Dijkstra, start from the target node and follow the back pointers. So after you run Dijkstras and you've created your table, similar to the table y'all created in question 2 of exercise 4, you want to follow the back pointers. And that's why we kind of had y'all kind of keep track of the predecessor, because if you keep on going back to the predecessor, so let's say you want to find the path from the source node A to node Z or something. What you would do is you would start at Z, go to its predecessor, and so on until you get back to the source node. And that will give you the shortest path between those two nodes. And this is kind of what the pseudocode is modeling. If we've never reached the target, meaning the target distance is infinity, then we return null because there is no path available between the source node, the source vertex, and the target vertex. And again, node and vertex are kind of used interchangeably. And right here, we're just keeping track of the path, keeping track of the current node. We add the current node to the path. And then in this while loop, we just continually get the predecessor, and we kind of retrace our steps to see how we got to where we are. And if we reverse the path, then we get the path from source to our goal. So this is what this pseudocode is kind of modeling. Cool. Now let's look at Dijkstras. So this is going to look kind of like similar to the exercise problem. So right here, let's say we want to start at vertex S. If we want to start at vertex S, then we can just mark it as processed. The distance from S to S is 0 because we start at S. It doesn't cost us anything to go to S. So that's why the distance to S is 0. So now that we have this first row kind of completed, why don't we spend maybe like 5 minutes, try to fill out the remainder of this chart here. So again, this is just problem 6A from the section handout. And then let's come back together and kind of like talk about the solution. All right, we are back. So we left off with problem 6A, Dijkstras, and just trying to figure out how we can like fill out this table. So can somebody help me out with what we do next? So we just process S and we know its distance is 0. What do we do next? What is next on the agenda?
We go to the smallest edge.
Yeah.
So 6, so we go to T.
Yeah, thank you. That's exactly what we do. So we noticed that we just explored S and we can really only go 2 places, right? We can either go to Y or we can go to T. But remember that Dijkstras is like greedy. It wants to pick the best possible choice it can go to. So it's going to go to 6. So we just fill this out. We just found a path to T. We found a path to Y. We update the values. We can go from S to Y in a distance of 7. We can go from S to T in a distance of 6. Fill it out. Mark the predecessor. And next, like Daniel was saying, we can now go to T because that's the next shortest path to go to. From S, you can either go to Y or T. Since the path to go to T is shorter, we go to T. So now we're at T. So now it looks like we have 3 outgoing edges from T. We can go to T to Y, we can go to T to Z, we can go T to X. So what should we be updating in this case? What's next? All right, S to Y. Could you elaborate on S to Y, Runying? T to Z. Yeah, so right now we are just trying to like fill out what's in the table. So what we would fill out now is, all right, we found a path from T to Y. However, the total cost from S to Y then would be 14 if we update this. Because we're saying if we go from T to Y, we have to add the total cost that it took to get to T plus the total cost from T to Y. So that would be 14. And since 7 is less than 14, the path from S to Y is lower than the path from S to T to Y. So we don't update Y. So what we do update though is the path from T to the path to vertex Z and the path to vertex X. Because currently it's set to infinity. But since we found a shorter path, T to Z only costs a total of 10 because 6 plus 4 is 10 and 5 plus 6 is 11. That's still shorter than less than infinity. So we're going to update X and Z. So we're going to update to 11. And again, 11 is going to be the total cost of going from S to T to X and S to T to Z. So S to T to Z is 10, S to T to X is 11. And the predecessor to x and y are both t. And notice how we don't update y here. And that is because the path from s to t to y would be 14. But since the current path to y is shorter, we don't update it. So we're going to pick the next shortest path. And I think this is what Runying was kind of alluding to earlier. This is the next path we explore. Now we go from s to y, because that's the next possible shortest path. And then we're going to see if we can update our values. So if it costs 7 units to go to y, then it must cost 7 plus 9 units to go from s plus y to z. So that's 16. Let's check if that's lower than 10. It's not lower than 10. So we're not going to update the value for vertex z. However, we will update the value for vertex x. Why is that? It's because if we go to x, starting from s, going to y, and then to x, the total path is 7 plus 3, which is 10, and that's less than what we currently have, right? So we update this to be 10. And then we're done exploring y, so we mark it as processed. So next, it looks like we have a tie, so we can just arbitrarily pick one of these. So let's say we pick x. So now x has one outgoing edge, and to get to t, it's going to cost 2 units. And the total cost of getting to x at this point is 10. So 10 plus 2 is 12. But right now, our current marked distance is 6. And that's better than 12. That's less than 12. So we actually don't do anything in this case. Nothing happens when we explore x. Next up, let's explore z. There's only one more vertex to explore. Z has one vertex to x. It has a cost of 7. So let's add 10 plus 7. It's 17. And 17 is greater than x. So again, we already have the shortest path. So nothing happens here either. So now that we kind of like explored every edge, every path, this is our resulting shortest path tree. So this is the shortest path to get to every single other vertex starting from s. If you want to go to x, the shortest path is going to y, then to x. If you want to get to z, the shortest path is to go from s to t to z. So that's Dijkstras. Any questions about this? If the node is already processed, why do we still need to compare that path? So if the node is already processed, you don't need to compare that path. And the reason is because we already know if it's processed, there's not going to be any possible shorter path to that node than what you currently have written down as processed. And that is a invariant of Dijkstras. As long as every single path is a non-negative weight, so 0 or anything bigger than 0, then you know that once you're on a new node, that's going to be the exploring a new node. That's going to be the shortest path to that node. Yep. But in the case where you're like kind of like checking, for example, at this point where we do nothing, we still want to check if the actually, let me correct what I said earlier. So right here, we still want to check if there's like a actually, never mind. Take back what I said. So yeah. So for instance, right here, x, if t was already processed, that means the distance to t has to be shorter than the distance to where we are at right now. right? Because the distance to where we are right now is 10. But if the distance to t was shorter than that, then we would already have found a shorter distance for t. So that's why it's marked as processed. So if it's already marked as processed, then you can just kind of like, you don't have to do the comparison anymore. But I kind of wanted to do the comparison in this demo to like really kind of like get that idea out there. And this all stems from like Dijkstras being a greedy algorithm and the invariance of Dijkstras, which I think we'll go over in a few slides. All right, cool. So here are the invariants of Dijkstras. Invariance, just review, that just means things that are always true at every single step of the algorithm. So here are the invariants. The predecessor is the best known predecessor of V. So at this point, the predecessor of V, this is the best known path to get of V. And this to V is the best known distance of S to V. So at each point, we always have the best currently known distance from the source to some vertex V. And the prior queue always maintains vertices based on dist2. So that just means that the item that you would remove from the priority queue, so I guess the item at the front of the priority queue, is always going to be the shortest path, the next shortest path available in your graph that you haven't explored yet. So yeah, it always visits vertices in the order of total distance from source. So it always finds the shortest distance possible at every step from the source. And you won't have to know like at a really deep level like why this exactly works. If you want to like kind of like get into the nitty-gritty proof of things, I would recommend taking like an algorithms class. But for this class, you don't really need to know exactly why everything works at a like really low level. You just have to know it works. And if you want to like get into the theory on why it works, an algorithm class is great for this. Cool. So now let's kind of like talk about BFS and Dijkstras. They're almost the same. They both find shortest path trees, but the shortest path defined in both of these trees is just slightly different. So in a BFS, graphs are unweighted. That means there's no edge weights between vertices. There's no numbers between the edges. Dijkstras, it is weighted, so these edges do have weights to them. So notice that these have numbers, these don't. BFS finds the shortest path in terms of the number of edges from S to every other node. Dijkstras, on the other hand, finds the shortest path in terms of the sum of edge weights from S to every other node. So Dijkstras, it doesn't necessarily find the shortest path in terms of the number of edges. It just finds the shortest path in terms of the edge weights, in terms of the cost. And then BFS finds the shortest number of edges. So you're crossing the least number of edges to get to every other node. But they're both shortest path trees. Any questions on this slide? All right. So again, there's more Dijkstras on the week 6 section handout from last week in the slide deck. Be sure to check them out. Dijkstras is a super cool algorithm. Now let's talk about something called disjoint sets. So this is a new kind of like ADT we're going to introduce. And at first, you're going to be like, hold on, wait a minute. This is kind of like useless. Why do we ever use disjoint sets? Like, what's the point of it? It's not really intuitive. Like, why do we use it? And we'll see why it's super powerful and super useful as we talk about a new concept, minimum staining trees. So right now, let's just review what a disjoint set is, and we'll see how it can be used in a future application in future slides. So the disjoint set ADT involves 3 main functions. So it has a make set function where it creates a new set within the disjoint set where the only member is X. Find set X, looks up the set containing element X, and returns the representative of that set. Union XY looks up the set containing X and set containing Y, combines the two sets into one, picks a new representative for resulting set. So this is kind of a mouthful. It's like, oh, like there's a bunch of representatives, elements, sets, a little bit confusing. So let's take a look at this little diagram on the bottom to see what this kind of even means. So let's say you call make set 2, right? When you do make set 2, your set is going to look at like this disjoint set on the bottom right here. So it's going to contain one item, which is 2, and it's going to be its own we call representative. Representative is just going to be like the topmost node. It's going to be at like level 0, and this will represent all the nodes within the set. This is kind of like the leader set or leader value. You can think of it that way. But every disjoint set is going to have one representative. And if we look at over here, we have another disjoint set, but this one, it has a representative 8 and has a bunch of nodes pointing to it. So what does that even mean? Well, if you call find set on, let's say 12, it will look up the set containing element X and returns the representative of that set. So find set X, it's going to bring you into this disjoint set over here to the left. And then it finds 12 right here, right in the middle. It goes all the way up to the very top level. And it just so happens that the top level is the direct parent, which is 8. And then it returns the representative of that set. And since 8 is at the topmost level, the representative that's returned is going to be 8. And when you call union XY, it looks up the set containing X, set containing Y, combines the two sets into one, and picks a new representative for the resulting set. So what this essentially kind of like looks like if you union like 8, or if you union like 12 and 2 together, what that will look like is, all right, 12, find the parent. Parent is 8. And then 2, find the parent. Parent is just itself, size 2. And since 2 is smaller, since this disjoint set on the right is smaller, it's going to join with 8. So 2 is going to end up pointing to 8. And that's going to be part of like one bigger set on this side. Now, at first, like this totally doesn't really make a lot of sense in terms of like intuition. Like, why would you use this? But we'll see a use case for this that's super cool, actually. So this is just going over some more examples. So big idea is we want to find out if two elements are in the same exact set. Are they in the same set? One way we can do that is we can, let's say we want to see if 1 and 7 are in the same set. From this diagram, you can tell that they're in the same set, right? But in order to do this in terms of code, you would call find set on 1 and find set on 7. And recall that find set, this returns the representative of the set that it is in. And the representative of the set that 1 is in is 8. The representative of the set 7 is in is 8. So that means they are both in the same set. Any questions so far about disjoint sets? All right. So now let's talk about union. So what does it mean to union? Union just means to kind of like join two sets together. You're unioning two sets together. So the steps involves a few steps. First step, use find set twice to find the two representatives. So recall, let's say we want to union the set that 1 is in and the set that 2 is in together. So first, you want to check which set 1 is in, and you use find set to do that. If you call find set on 1, you'll know that find set is in, or 1 is in the set that in which 8 is the representative. And if you use find set on 2, you'll know that 2 is in the set in which 2 is the representative. So clearly, they're in two different sets. So step 2 is then stick one representative under the other. And the way we kind of like make this choice is we just determine, all right, which set is smaller. In this case, the set that 2 is in is smaller. So 2 is going to end up pointing to 8 instead of 8 pointing to 2. So notice how right here in step 1, there are two separate sets. But then in step 2, we point 2 to 8. So now 2 is no longer representative. 8 is now 2's representative. And let's talk about some optimizations that make this a little bit faster. And I kind of like hinted at this earlier, but trees can be unbalanced, right? If you join like in the worst case, we kind of talked about how trees can be a linked list. So one way that disjoint sets kind of like try to get around this is using size. So size, is always going to upper bound the height of X. Why is that? It's because in the worst case, a tree is going to be a linked list. So the height of that tree would be the size of the list. So the size, we know, is always going to upper bound the height. And again, a lot of this like kind of like theory stuff and optimizations, logic is discussed in algorithms classes. So highly recommend those classes if you want to check it out. And so since we know that size upper bounds the height of the tree, we can use size to kind of like optimize which representative, when we join two sets, which becomes the new representative. So we would keep track of the size of all the different trees and all the different disjoint sets. When unioning, we make the tree with larger size the root. So in this case, this tree on the right has size 4. And 2 is the representative. So 2 is going to remain the representative because it's bigger than the tree that you're unioning by. And if it's tie, you can just pick one to the root arbitrarily in your code. Doesn't really matter if there's a tie. The second optimization is when we do find set 15, we can tie all nodes seen to the root. The additional cost is insignificant because once you connect it, it just makes everything a lot faster. So what that means is if we try to find sets of the 15, if we want to try to find the representative of 15, notice that we would have to go up to 15's parent, 11, go up to its parent, 5, go up to its parent, 1, and then go up to 1's parent, 0. And notice how if we keep on doing this, then it's kind of like a little bit annoying, right? It kind of like runs in like log n time. So what if we were to do something like this? What if instead of, after finding the parents, instead of having like 15 point back to 11 to 5 to 1 to finally to 0, we just point each of these nodes back to the parent. What this does is it allows us to instantly get the parent without having to traverse back up the tree. So without the optimization, every time you call find set of 15, you would have to go up to 11, up to 5, up to 1, up to 0. But with this optimization, now you can, after calling find set for the first time, you can go from 15 to the parent 0 instantly. So this essentially just saves you a few steps. Instead of like having to go through the normal route, going up to your parent, up to its parent, etc., up to the root, you can just take a detour and go straight to the parent. And this saves a little bit of time. So that's the second optimization. And here's an array disjoint set implementation. A map stores the item, so the index in our array representing the disjoint sets. and the array in which each index represents the item from the map. And the value at the index is either the index of that item's parent, or if the item is the representative of the set, -1 times size. So here's the map, here's the array, and here's kind of like what the disjoint set would look like. So we put in -3, 0, and 0. All right, cool. So any questions about disjoint sets at all before we move on to some practice problems? All right. So problem 4b. Let us do this as a class together first, maybe. So let's just do 4b together. So when we do union 2 and union 13, what do y'all think we should do? What are the steps we need to follow? So what is, I guess, the first step? Yep, the first step is going to be find set. Exactly. And we're going to need to call find set on both pass-in parameters. So we're going to need to call find set on 2 and find set on 13. So find set on 2, that's just going to give us this set over here with size 1, where the representative is 2. Find set on 13 is going to give us this set over here, this tree over here, where the parent is 7. So now that we found the set, how do we actually join them together? What is that going to look like? So now that we found the set that 2 and 13 are in, what does it look like to join them or union them together? Does 2 go to 7? Does 7 go to 2? Yeah, 2 goes under 7. 2 points up to 2. Yep, exactly. So we found the sets, and now 2 is going to point up to 7. How do y'all know that? How come y'all are so smart? How come 2 points to 7? Yep, exactly. The key point here is the smaller sizes points up to the larger size. So since 2 has a size of 1 and 7 has a size of 2, 2 is going to point to 7. Awesome. So this is what we have now. Now we started with 4. Now we have 3 trees. Now let's union 4 and 12 together. So again, we follow that same process, right? First, we're going to find the set of both of the parameters. So if we do find set on 4, we know that 4 is in the set 6. 6 is the representative right here on the left. Find set on 12, it's in set 8. 8 is the representative. Oops. So yeah. So now following that same kind of like logic as before, since set 8 is smaller than set 6, 8 is going to point to 6. Cool. Is this the final tree after we union them together? Is this it after unioning 4 and 12? Yes, I think so. Yeah, so we're actually going to be missing one more step. So remember the second optimization? The second optimization was right now, we just called find set on 12, right? So 12 is gonna find its parent 11. 11 has a parent 8. So now we're gonna move 12 so that it's pointing to 8. So next time you call find set on 12, it doesn't have to do this extra step, saving some time. So we were just missing that one thing, but otherwise everything is good. Path compression. So now, hopefully it's a little bit clearer that if you call find set on 12, this takes up one extra, I guess, piece of work than this. This goes straight to the parent. This has some intermediate nodes it has to go through. And nothing changed with 4 because 4 was already pointing to 6. Cool. Now, this is what it looks like after you kind of like format it more in a prettier way. Looks like that. Before, after. Before, after. Now let's union 2 and 8 together. So 2 and 8, we find set of 2, found it right here, find set of 8, it's right here. And we don't do any path compression because in both nodes, we just went straight to the parent. 8 went straight to 6, 2 went straight to 7. And then we point 7 to 6 because 6 is much bigger than 7. And we're done. This is the final set after we joined everything together. If 12 had children, would the children also point to 8? Yes. So in this example, let's say that, let's see, 12 had, if 12 had children. So no. So if 12 had children, so like maybe 13 points to 12, then its children wouldn't also point to 8. Only 12 would point to 8. And the reason is because we always start at 12 and we move up. We always start at this node and we move back up. So we're not able to change the references of its children. And that is kind of like what we get into with this second problem right here. 2 and 8. Notice that 8 has 4 children, right? 9, 10, 11, 12. Even though we call find set on 8, it doesn't change its children at all. Its children still point to 8, and its children don't point to 6. That's a great question. Cool. Any other questions before we move on to MSTs? All right. So let's talk about MSTs. MSTs stands for minimum spanning trees. So here's a vocabulary slide. A tree, when talking about graphs, is a connected acyclic graph. So in this example, we see an example of tree. These are all examples of trees, but this particular example. Notice that there's no cycles. That makes it a tree. A tree is just a graph with no cycles. A spanning tree are a set of edges that connects all nodes of the graph in a tree. So in this middle graph, notice that how all the edges are connected, right? And it's connected via the edges 4, 5, and 2. A minimum spanning tree is just like a spanning tree, but with additional requirements. The spanning tree, it is the spanning tree of the lowest possible total weight. What that means is if you sum these weights together, 4 plus 1 plus 2, that's going to be the smallest weight possible in order for you to connect every single node inside this graph. So that's what a minimum spanning tree is. And there's going to be multiple algorithms that are used to find MSTs. In particular, there's going to be two that we're going to be talking about. We're going to be talking about Prim's algorithm and Kruskal's algorithm. So one key difference that we want to point out though between is MSTs and SPTs. They sound very similar, but there's a key difference. They sound the same. A shortest path tree depends on the source vertex. So with shortest path trees, you always start from some starting vertex. So let's say you start from A. The shortest path tree is the shortest distance to every single node in the tree from the node. However, for MSTs, it's a little different. There's no concept of a source vertex in MSTs. It's just the tree that minimizes the total edge weight such that all of the nodes or vertices in the graph are connected. It doesn't have a concept of shortest distance. It just minimizes the tree's total edge weight in which every single node is connected to each other. Cool. Any questions so far? All right, cool. So this is the diagram from earlier. Now we're adding Prim's and Kruskal's algorithms. So both finds the shortest path trees in BFS and Dijkstras. Prim's and Kruskal's, it finds the minimum spanning tree. And difference is things are weighted, undirected, and it gets the lowest cumulative weight for the whole tree in which every single vertex is connected. So here's a high level kind of idea of each of these algorithms. With Prim's, you start with a tree from a single node. In each iteration, you connect a node in the tree to a node that's not in the tree with the cheapest edge possible. And you slowly build up one connected tree. So if you kind of want an analogy to Prim's, let's say you're traveling, right? And for some reason, every time you go to a new location, your money resets or something. Let's say you start from one location, you start at one city, and you want to go to all of the cities where all the cities are the vertices. At each city, you want to go to the next city in terms of which city is the cheapest to go to at that point. That's essentially what Prim's is. You start with a node, you connect the node to a tree, you connect a new node that you haven't explored yet to the nodes that you've explored already, and you pick the cheapest edge at each iteration. So it's a little bit like Dijkstras, except you don't have a source node. And in Kruskal's, you repeatedly add the smallest edge that doesn't cause a cycle in the tree you are building. And you can build a few disconnected trees before they all merge. So Kruskal's, the way they kind of describe it is that think of it as you're building up a big forest. And in the end, you're going to combine all of the forests together into one big forest. But in Kruskal's, you kind of just build one small forest at a time. Cool. And in Prim's, think about nodes. All right, at each node, which is the cheapest node I can go to? Think about, in Kruskal's, you want to think about edges. What is the shortest edge I can take at each step? And here's a bunch of pseudocode for Prim's. Not going to go over it too much. The high level idea is all in here. This is just the pseudocode for it. Kruskal's, again, here's some pseudocode for it. And look at that, disjoint sets. So with Kruskal's, it actually uses disjoint sets for each vertex in G. And we'll be showing an example of how disjoint sets are actually used for Kruskal's in a few slides. So let's go over Q1A, Q1C, and Q2. going over some minimum spanning tree practice. And let's first start off with Prim's algorithm. So with Prim's algorithm, I think they're missing a slide here. But at Prim's algorithm, you just pick a node to start at, because eventually you're going to want to visit every node, right? So you're just going to want to pick whichever node you want to start at. So let's say we start at A. So with the next step is to just kind of like fill this out. And notice how this is almost exactly like Dijkstras. Prim's is almost exactly like Dijkstras. I would argue a little bit simpler. So we start at A. This is to A is 0. Mark it down. It's processed. Yes. And now we explore, all right, what are the possible nodes I can go to from A? So I can go to B. I can go to C. I can go to E. So next up, I'm going to choose to go to B, right? Because that's the shortest distance or the shortest node I can go to that costs the less. So I go to B. And now at B, I can go to C and I can go to D. So the distance from B to C is 3. Previously, it was 7. And since 3 is less than 7, we update this to be 3. If this were Dijkstras, you would have to add the distance to B plus the distance from B to C, which is 5. But for Prims, you just get the distance directly. So you don't have to add 2 plus 3 and get 5 over here. It's just going to be 3. So that's why I think it's a little bit simpler. And then likewise, you just found D, so you mark it down as 4 because that's the distance from B to D, 4, and this is the edge. So next, you would explore C because that's kind of like the next shortest thing. And now we update the value to vertex D to 1 because the path from C to D is 1, which is less than 4. Again, you don't have to keep track of like previous distances. You're just going to get the immediate distance from the node that you're currently on to the new node. So you can go from C to D in a distance of 1. And then we just found E again, and that's shorter than 8, or that's less than 8, so we update it to 5. Next, we go over to D. All right, so now we're at D. We can go to G in distance of 10. We can go to or we're going to go to G in a distance of 10, and we can go to F in a distance of 6. So D to G is 10, D to F is 6. And now we're at E. So E, the distance from E to G is 9. So we update the vertex to G, the distance to be 9. Previously, it was 10, and that 10 comes from D to G. But E to G is shorter than that, so we're just going to take E to G instead, which is 9. And then D to F is going to be 6. And then next up, we look at G. G going from F to G is 0. So we're just going to mark that down. And finally, now that everything is processed, we have the minimum spanning tree. Cool. Any questions about this problem? And again, don't worry about like if you don't like fully understand like why this works. In this class, you don't really have to know why it works. You just have to kind of like know the algorithm, get a high level understanding of it. If you want to like know why these things work, again, algorithms is a great class for that. Cool. So hopefully you can see with prims, you basically just go down your list of nodes and then you just find the shortest distance at each step. So in the beginning, going from A to B was super short, T, then we went to C, then D, etc. So you just want to start from one node and then take the next shortest path you can take to the next node. Cool. So now let's think about unique MSTs. So in this MST, or in this in this graph, there's only one minimum spanning tree. Is this the case in all graphs? Is there only ever one minimum spanning tree? What do y'all think? Can there be multiple minimum spanning trees? Yes. Yep, you're correct. There can be multiple spanning trees. The reason there's only one MST in this example is because all edge weights are unique. But in the situation where you have like multiple of the same edge weight, so let's say we have like A, B, C, D, or something like that, and each edge weight is 1, then you can have like 4 different minimum spanning trees in this example. You can have something like this. You can have something like that. So in the situation where there's only one MST, all edge weights are unique. However, in some cases, when edge weights are the same, there might be more than one MST. But either way, the cost of all MSTs are going to be the same by definition. All right, cool. Now let's talk about crusticles. So prims is one way we can find an MST. So let's talk about crusticles and how this works. So crusticles uses disjoint sets. And using disjoint sets, why do we use it? It's because it makes things a lot faster. So here's the pseudocode for it. So first off, we create disjoint sets for each vertex in G. So every single vertex is going to be its own kind of like disjoint set. Done. Then we sort the edges by weight. So this is going to go into like a priority queue, sort the edges by weight. And then for each edge UV in sorted order, if U is not in the same set as V, join set U and V. Add edge UV to MST. So what the heck does that even mean? That just means that if 2 of these nodes are not in the same set, then just add them to the same set. And since we're going in the order by weight, we're going to start off with looking at C and F, because the weight from C to F is the same, or the weight from C to F is the shortest weight, 1 in this entire graph. So since C and F aren't in the same set initially, we add them into the same set, right? So now C and F are in the same set, as you can see. And then we join them together. And this is currently in our MST. Then we get the next shortest edge. So in this case, there's 2 edges we can choose from, D to G and E to A. Our algorithm should just arbitrarily pick which one we want to pick. So let's say we go from D to G. So D to G is the next kind of set we're unioning together. And we're just going to follow this process until we get a minimum spanning tree. Next up, we join A and E together. And then the next one is going to be D and B. D and B. And then the next shortest edge is 4. And however, we don't want to add E and F together because they're already in the same set, right? E and F are already in the same set. E, C, F, A. They're all in the same set. So we're just going to ignore this edge right here. So again, we don't add this edge either. A and C are in the same set. And then we don't add this edge either because G and F are also in the same set. We don't add this edge either because C and D are already in the same set. And this is our minimum spanning tree using crusticles. So the focus of crusticles is you want to sort all the edges by edge weight, and then you want to pick the next smallest edge, and then see if you want to connect the 2 nodes that this edge connects. And the way you do that is using disjoint sets. Disjoint sets make this a hell of a lot faster. And that is why we went over it in the beginning. But cool. So that's about all the time we have left for section. Are there any questions before we go?